Okay, so I'm just going to go over how to apply the calibration files. So I'm going to do this just from the device, so not using SFTP, just to show what's going on. And I'm also going to show how to edit the interpreter for the files. So the first thing we'll do is I have not logged into this yet, so I'm just going to go and look at the calibration files and see what's. Let me just mute this and see what is there already. Okay, so there's lots of calibration files, and clearly we want the ones with today's date on it. So what I'm going to do is we don't have to use all of these, and even if they all exist in the same place, I'm just going to copy all of them into the directory where we want to work with them, which is the backup directory. Oops, sorry, opt, PMS app, backup, cal, and we can copy them all in there. Oops. So we have to copy recursively. Huh? Okay, so all the calibration files are in there. Now what we're going to do is just take note of what the name is. So the name is the same as it was before, but now the new one is 3020. So 3020 on all of them. So what I will do is I'm going to go back and I'm going to go into the hardware mod. And then we're going to go into hardware access client. So the hardware access client is where the interpreter is, or the interpolator. So I'm just going to take a screenshot of these so I can remember what they are. So you can see that we have a file called interp. So I'm going to nano interp. Okay, so this is pretty straightforward. What we're going to do is that we have 7 total sets of data, and I'm not sure what the group length is yet. I'll show you how to determine that, although it is based on just how the calibration file was set up. And then we have all of these, which is what we really want to change. So what I'll do is I'll take a look at our SNP. This is just if I'm unsure of what the temperature step is. What I can see is the temperature step's the same. So all I need to do is change these to 3020 instead. So if you had more or less of these, you would add them here, and they have to be in order. So the lowest temperature has to be the first one, and so on. Okay, so those have all been entered. If we go to the bottom of the file, what you can see is that there's some testing here. And again, this stuff just runs on its own. So this is a great way to test it, to see if it fails. If there's some kind of failure, it'll usually tell you. So I'm just going to run sudo python 3.8 and interp. And if there's errors, we can fix them, and I'll explain how to fix them. So you can see that it said no such file in directory. So it's missing the band 1 minus 30 for this. So I'm just taking a look right now to see where it is. So so minus 30. Okay, so what we're going to do is we're going to go, and I'll show you what that problem was. So it didn't find anything. what you can see here is that I have a test directory, and then I have so base dir is where the files are located, the calibration files. So I'm going to uncomment this, and I'm going to put that one. And we want this one because this is where the calibration files are located. So if I have testing files, sometimes I'll stick them somewhere else. In this case, I don't have any testing files, so I'm just going to use the main ones. Oops. Okay, and now you can see that we have some values printed. So these values may make sense. It printed them successfully, which is nice. It means that there aren't any errors. What I'm going to do now is I'm going to show what matters and how this works. I'm just going to walk through the code, and hopefully, if there are questions afterwards. So the first thing is the group length. So that's how many samples there are in a particular set of data. So that's how many power steps, essentially, which is what we care about. These are fixed, so this is the position in the vector that contains the dBm. This is the position that contains the voltage, frequency, temperature, etc. And then these we just leave blank. Here's where we load our band data. If we have more of them, we change this number and we load the rest. So you can see that we're adding them as elements in a list, 0, 1, 2, 3, 4, etc. And we're loading the files. So that's how this works. But in this case, we only have 7 of them. And the AutoCal system is going to get rid of this feature and just make it so it scans the directory and looks for files and develops a working file set. So that's kind of one of the main features of the AutoCal, is creating a unified calibration file format that has the description in it, so we can get rid of this stuff, because this is really annoying to do because it's a lot of manual code entry. Okay, so there's a couple functions. Find nearest that's nothing special. That's just a general purpose function. So get band data is important. What you do is you pass this function the frequency and the temperature that you're interested in, and it will return all of the data that is in that band at that temperature. This is just used for the interpolation. You don't use this anywhere else. Get lower bands. This is going to get the frequency below the frequency that you're at. So if you're at 700 megahertz, it's going to look through the calibration and find whatever's below that frequency. And then we also have, and you can see that it returns 2 things. So it's going to return the upper band and the lower band. So if you have 700, it's going to return 698 as well as 702 if you're doing a 2 megahertz step. And it returns all the data in that band so that we can do linear interpolation between the frequencies. Getting the amplitude, that one's pretty straightforward. So we put in the amplitude as volts, and it does the same thing. So it looks at the top value and the bottom value, and then returns those as a tuple. Get band temperature. That one isn't used anymore. That was legacy for when we had multiple temperature sensors and we use the average of those temperature sensors. We don't do that anymore. Now we're getting into higher level functions, which just call the functions above. So we're solving an amplitude value. We're interpolating between 2 frequencies. That's what this one does. So we give it the target frequency, the dBm lower and dBm upper, and then the upper band and the lower band data, and it interpolates between those. And again, that's that one's linear interpolation. So then interp amplitude, this is the second highest level function. So you pass it a value that you want. So the solve val, so for example, you would pass in the voltage. So we'd pass in 1.1 volts. We'd pass in what frequency we sampled. So again, this is looking as if we're looking from the RF board. And then we pass in the solve frequency. So if we want to solve for 1.1 volts at 302.15, whatever. So this can be any number that is in the frequency band. And then the temperature that we have. So then it's going to solve that based on the temperature. And now we have the full interp. So the temp here is mostly ignored. It just goes by the base request. So you can see up here we have solve val and solve freq, but we don't have a solve temp. So solve temp means that we're also putting in the solve temperature that we want. So for this, I would just say solve val, solve freq, and then I would put in the temperature of 30, for example. It would not interpolate anything with temperature. It would just get the closest temperature value. So here, what we're looking at, and this function would have to be edited. So we're doing a full interpolation with a solve val, a solve frequency, and a solve temperature. So we pass in that we're currently at 23.1 degrees, and it's going to interpolate that temperature now. So what you can see is that here we have a list. So we're saying for I in range of minus 30 to 60 plus 15, the plus 15 is just to handle the index. With the step of 15, we want to solve the frequency at that value. And if you print x and y, which we'll do, you're gonna see how it solves every single value. We're gonna create a polynomial out of those values, and then we're gonna solve that polynomial and return the final value. And then calculating cable loss we don't do anymore. So I'm going to save this and run it, and what you'll see is now we're going to see those values being run. Okay, so let's take a look at this. So what we're going to see here, and I just want you to focus on this, is we have one list of data here, and then we have another list of data here. So these are the temperatures that these values were resolved at during calibration. This is important because even though the calibration was done at 15 degrees, we don't care. We only care about what the board thinks the temperature was. So here, even though it's minus 30, the board thinks it was minus 18. The reason it thinks it's minus 18 is usually because the board was warmer, and maybe there's some inaccuracy in both the temperature chamber as well as the board's temperature sensor. And you can see all of the different units that we have here. So all the way up to 70 degrees. And then here we have how the dBm values were solved. And this is neat because it lets you see the difference across the temperature range. So here you can see that at minus 18, it was 16.35 dBm, whereas at 70 degrees, it was minus 15.1. So there's 1 dB difference across that whole range. Now we can also look and see this value is the base value. It goes down, 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 and it goes down. So that's good because it means that our polynomial is going to have an excellent fit because the values aren't going up and down, which means that the interpolation that we're using, the polynomial interpolation, is a good choice. And then we have our final values over here tested at each frequency. Once that's done, so we've edited our interp file. So if we want, we can just copy the interp file instead of copying everything else. So let's do that. So you can copy the entire hardware mod directory, which I think I demonstrated before. Excuse me. So I'm going to go into the hardware access client where I just was, and we're going to sudo cp the interp, and we're going to copy it to opt, pms app, software mods, hardware mod, and hardware access client, and we're going to copy it there. So the dot means copy to this location, and we're going to have been replacing that value. So now what we can do is we'll go to the home folder, we'll take a look at what's going on here. Okay, so you can see that all of the modules are active. Okay, that's interesting. So again, the hardware module should always be stopped whenever a calibration is running. That's interesting. Okay. So because we copied a new Python file into the hardware module, we have to restart the hardware module as well. That's very important. So the hardware module does take the longest to start, and then once it's started, here we go, and I think there's probably a signal generator connected, so let's do that. and the signal generator is connected at 91. So this is 73 though. Ragdoll test, I'll set it to 350, 86, and 0. And this will throw an error if it does not connect and the IP is bad. The error is just the default error, so it's not usually very descriptive. So I guess the IP that I have is incorrect, so I think it is 74. Connection refused. Okay, that's interesting. All right, so I cannot connect to the Ragdoll to fully test the calibration, but we do know that the calibration is correct. So there's one more test that you can also do, which I'll just do while I'm here. So let's go back in here to test out our calibration file. So we're going to go to repos again, and we're going to go to cal. Okay, so we're going to go into, sorry, my mistake. We're going to go into the hardware module, and we're going to go into hardware access client, and we're going to nano the interpreter. So what we'll do is we'll get rid of these, and we'll put these in. And what you can do is you can leave it the same, and this is just a good double check, which eventually the software will just do automatically. But what we want to do is just we want to have the values decreasing. It doesn't matter by what values. We just want to make sure that the interpolator is going to actually do this correctly, and we should see the values decreasing. So here you can see that we start at -5, -10, -16, -21, -28, -33. Now I'll show you why this could be a problem. So let's say that we got this number wrong, the group length, and this is a very important number, and we run it. What you can see is that we have a problem now. So you can see we have -20, -20, -20, -21, -28, -33. Something's very wrong because these values should be going down. So the interpreter still works because the data is still aligned, but it's aligned improperly. So this has to be correct, and that's just a good sanity check. So yep, so everything should be working now. I can't connect to the signal generator. Let me just try actually. Actually, 491. Okay, the email says it's at 7290, but with the subnet, that probably won't reach. Yeah, so I'm not sure what the, oh. Okay, well there's something there now. I'm not sure if somebody's doing this or what, but yeah. Anyway, it should be functioning. Yep, I hope this was